Hofmann and Saytzeff elimination are among the most important topics for JEE and NEET exams. Whenever a reaction follows the E2 mechanism, students often get confused about whether Hofmann products or Saytzeff products will form. In this video, I will explain a simple and logic way to decide between Hofmann and Saytzeff products. I guarantee after that you will never be confused again. And if you think that you already know this topic very well, so this is the challenge for you. Solve this before watching this video and post your answer in the comment box.
So let's start this video. Once you are 100% sure that the reaction is following the E2 pathway, then there are two possibilities. First one, that it could give Saytzeff product, which is more substituted alkene, or it could give Hofmann product, which is less substituted alkene. For Hofmann product, I will tell you the two conditions. If you see those two conditions, then always remember that you will get the Hofmann product. So first one is when you see that leaving group is bulky. When you see that the leaving group is bulky, such as trialkyl amine, it could be ethyl or methyl. In that case, you will get the Hofmann product as a major product and the Saytzeff will be minor, irrespective of the size of the base. So remember that if you see such leaving group which is trimethyl ammonium ion, then remember that you will get the Hofmann product as a major product. And the second condition is that when there is a bulky base such as tertiary butoxide and hindered substrates, in that case accessibility dominates over the stability. So you will see which proton is easily accessible. Then you will not think about the stability of the alkene. So we will learn the logic behind it step by step. So let's look condition first. So why you are getting the Hofmann product as a major and Saytzeff as a minor, we can understand through the Newman projections. So we know that in E2 elimination reaction, beta hydrogen must be anti-periplanar to the leaving group. This is the structure of the starting material, and I have labeled two beta hydrogens, this one as a red color and this one with the pink color, and this is the labeling on this carbon. So now let's draw the Newman projections and conformations for the Saytzeff product. So this will be the conformation for this Saytzeff product. So look at this. This is the carbon number 1. This is the carbon number 1. This dot is carbon number 2, which has this bulky leaving group, and this big circle is carbon number 3, which has this pink hydrogen and methyl. So there is a methyl. So when you put beta hydrogen anti-periplanar to the leaving group, then you get this kind of conformation for the Saytzeff product. And if you see that there is a gauge interaction between this methyl group, which is present on the carbon 3, and with this bulky leaving group. Due to this interaction, the transition state has very high energy, and hence this is unfavorable transition state. Now look at the conformation for the Hofmann product. In this case, this is the carbon number 1. This big circle is the carbon number 1, which has 3 hydrogens. So this is the 1, 2, 3, and we have to arrange this hydrogen in such a way that it should be anti-periplanar to the leaving group. So this is the anti-periplanar. Now carbon number 2 is here in front of you in the form of dot, which has leaving group, 1 hydrogen and ethyl group. So this is carbon number 3 and 4. This is ethyl group. Now look at this. In this conformation, which is for the Hofmann product, in which you want to abstract the proton from the carbon number 1, hydrogen is close to this bulky group. So there is no gauge interaction. Therefore, this transition state has low energy, and hence this is the favorable transition state, due to which in this case you are getting the Hofmann product as a major product. So remember that whenever you have a bulky group, then in that case Hofmann product will be major, because in the transition state it has low steric hindrance. It has less steric hindrance and hence low transition state energy. Therefore, this is kinetically controlled product. Okay, now I hope it is clear to you. Now let's move to the condition number 2. So let's take an example. This is 2-bromo 3-methylbutane and this is reacting with tertiary butoxide. This is potassium tertiary butoxide. So potassium tertiary butoxide is highly hindered base, and when it tried to go to abstract the proton from this beta hydrogen which is sterically hindered, then there is a problem because this substrate itself is a sterically crowded and this base is also sterically hindered. But this hydrogen which is on the primary carbon is easily accessible. Therefore, you will get the Hofmann product as a major product and Saytzeff will be the minor product. Now, if you decrease the steric crowding at this carbon, for example, if you make this kind of substrate and in which you decrease the steric crowding at this position, what do you think? What could be the product? Still, you will get the Hofmann product as a major product because this base is highly hindered. So remember that whenever you see the tertiary butoxide base, so you will make the major product less substituted alkene. Remember that accessibility dominates over the stability. So this carbon hydrogen is easily accessible as compared to this secondary carbon. So now I hope those two conditions are clear to you. So now if you don't see those conditions 1 and 2, then always go for the Saytzeff product. Always go for the Saytzeff product if you don't see bulky leaving group or bulky base. Now for example, you are taking the same substrate 2-bromo 3-methylbutane which you have taken in this case, but now we will change the base. We are changing the base from tertiary butoxide to alcoholic KOH, and alcoholic KOH is a strong base and its size is also small. So therefore accessibility for this beta hydrogen and this beta hydrogen is same for this base. So what it will give? It will give you more substituted alkene which is the stable alkene. So you will get the Saytzeff product as a major which is more substituted alkene and minor would be Hofmann product. Now let's take another example. In this case you have 2-bromo 2-methylbutane alcoholic KOH. So again you have less hindered base, so you are going to get the more stable alkene as the major product, and that would be Saytzeff product, and this will be minor product. Now this is the question for you. Post your answer in the comment box. Now it is a time to do the practice. So I have taken the two examples from the JEE Main. So let's solve this question. In question number 1, you can see that this is the sodium methoxide which is a strong base and it is a strong nucleophile as well. So there is a two possibility that reaction is following SN2 or E2 pathway. Since there is a steric crowding at this place which is quaternary carbon and this is also secondary halides, therefore this reaction will not go through the SN2, rather it will go through the E2 pathway. So now you can see that since the reaction is following the E2 pathway and we have a strong base and which is not hindered, at this position there is no beta hydrogens, only one beta hydrogen is available which is here. So we will make the product by removing this beta hydrogen and you will have this kind of product which is matching to the option B. So this is the correct answer of this question. What if you have, suppose if you have this question in which PR is above the plane, methyl is also above the plane and the hydrogen is below the plane. Instead of methyl, let's say you have a hydrogen here and you are using the same reaction condition, sodium methoxide. Then in this case you have one more beta hydrogen and this beta hydrogen is anti-periplanar to the leaving group. Hence you can remove this hydrogen to get to get the more substituted alkene, which is the Saytzeff product. So you will have this as a major product and this will be minor product, which is Hofmann. Now let's look at the second question. In this question they are using sodium tertiary butoxide, which is bulky base, and you have leaving group mesylate. This is called mesylate, and this is very good leaving group because negative charge can easily stabilize through the resonance. This is the structure, so this negative charge goes here and here, so it is very good leaving group. But the base is bulky, so base is bulky, therefore what is going to happen, it can't remove this proton, so it will remove this one. As I told you in the previous slides that when you have bulky base, then it will try to abstract the less hindered hydrogen. So what you are going to get in this case, then alkene will be this one. This will be the major product, which is according to the Hofmann. Now next step is the ozonolysis and oxidative condition. So just put oxygen this side and oxygen this side. Since this is oxidizing agent, therefore it will convert the carboxylic acid because you are using the oxidative condition. Therefore you will have this carboxylic acid and this will be formic acid, which is option D. Now look at this. This is the bulky base here. This is nothing but tertiary butoxide, and we have to make Hofmann product, right? But here is only one possibility, because this is the leaving group. Tosylate is the leaving group. Tosylate, mesylate are very good leaving group like iodide and bromide. So look at this. Tosylate is above the plane and there are two hydrogen. One is this one, which is below the plane, and another is this one, which is above the plane. And we know that the beta hydrogen should be anti-periplanar. So which is anti-periplanar? This beta hydrogen is anti-periplanar and this is not. So therefore you are going to remove this beta hydrogen. So what you will get? You will get this product. There is only one possibility. So there is nothing about Hofmann or Saytzeff. There is only one possibility, that this is the only beta hydrogen is available, so you have to remove only this beta hydrogen. This kind of structures are restricted about rotation around carbon-carbon single bond. Therefore you can't give rotation, and hence you have only one possibility to remove this beta hydrogen. Now we are going to look on some exceptional cases where substrates have restricted geometry, and geometry will decide the outcomes, not the base. For example, in this case, if you see that this is sodium methoxide base and we are thinking it should give more substituted alkene by removing the hydrogen from this position to give the double bond at this position, but we can't give the rotation about this CC bond, and hence there is a hydrogen beta which is not anti-periplanar, and hence we can't remove this beta hydrogen. But there are two beta hydrogens and we can remove one of them to give this less substituted alkene as the major product. So you can see that this is the Hofmann product. Now look at this option. Here is the situation is same. This sodium methoxide can abstract the proton from this carbon, but the problem is that we can't give the rotation around this C1 and let's say this is C2 carbon. So this compound has restricted geometry, therefore this hydrogen is not anti-periplanar. You can't bring it to the anti-periplanar. and hence the base will prefer to abstract the proton from this side, and then you will have less substituted alkene as the major product. So you will get this major product, or it could be exclusive also. So these are the exceptional cases where geometry decide the outcomes. So please remember these kinds of examples. Now we are going to talk about another exceptional case. Now second exceptional case where conjugated alkene dominates over isolated alkene. For example, if you have this kind of substrate and you are using tertiary butoxide, which is a strong base, and hindered base, so there are two beta hydrogen, one is this and another is this one. So if you remove this beta hydrogen, let's say A, and this is B, so you remove A. So when you remove the A, you are getting this product after removing the A. But when you remove the B, after removing the B, you will get this one. Now if you look at this compound, for this sodium for this base, steric hindrance is same at both the positions, and therefore it can abstract the hydrogen A or hydrogen B as well. So there is no discussion about the steric crowding in this case. But now we have to understand the stability of the alkene. So which alkene will be more stable? Stability of alkene. Two types of alkenes are more stable. One is substituted alkene and another is conjugated alkenes. And remember that conjugated alkenes are more stable than substituted alkene. So whenever you get the chance to make conjugated alkene over the substituted alkenes, then make conjugated alkenes. So here this one is more stable and this one is less stable because of the conjugation of the double bond, but substitution is same here. Okay, now let's look another example where we have to talk about that conjugated alkenes is more stable than the substituted alkene. So let's say you have this example and you are using a base. Now there are two beta hydrogen, one is this one, another is this one. So if you abstract this beta hydrogen, let's call it B and let's call it A. So after abstracting hydrogen A, you will get this one, in which this double bond is in conjugation, and if you abstract the B, then you get this one, and this is more substituted and this is less substituted. Let's call it, this is tri-substituted, this is tri-substituted, this is di-substituted. So which one will be major? So the major will be this one, because here double bond in conjugation. So remember that whenever you can bring the double bond in the conjugation with something, then that will be the major product, because conjugation dominates over the substitution. Now I am sure that E2 elimination is clear to you, and it is also clear to you when you will get Hofmann product and when you will get Saytzeff product. And remember these exceptional cases also where you don't need to apply Hofmann or Saytzeff rules. If you have any further doubt, ask me in the comment box.